Welcome everyone to this edition of Quantum Marketplace. This is the QED-C webinar that showcases QED-C members and helps to inform the public about the coming technologies, the products, the businesses that are out there, and the applications of quantum information science and technology to real-world practical applications. We have an all-star lineup this month. I'm really excited and looking forward to it. The focus is on quantum networking, as you can see on the screen. And sometimes it feels like quantum computing is taking all the oxygen out of the room, but there's a lot going on that's relevant to networking computers, but networking other things as well. And so I'm looking forward very much to hearing more about the various technologies that are coming to help enable that networking to happen. So with that, I will turn it right over to Mark Wippich, our moderator. Thanks, Mark.
Great, thanks, Celia. Okay, so just to touch point on some webinar logistics and format. So all the speakers, well, everybody will be muted except the speakers. Please send your questions in the chat window so the speakers and others can answer your questions. And then also, recording of this webinar will be posted on YouTube in the future, as with the other webinars. Okay, in terms of how we're going to do the agenda, we're going to first, I'm going to give some updates on the quantum marketplace itself, and then just a quick snapshot of networking trends and overview, and then the quantum networking lineup. So that's who we have today, this cohort, which is very exciting and leading companies in the space. And then also, we're going to migrate to a roundtable panel discussion, and then I'll give a snapshot of the upcoming webinar schedule. So people ask, what is the quantum marketplace for it? Well, it's really for the companies that are participating in the audience to raise brand awareness, facilitating collaboration, deals, and partnerships. And that's what it's been doing based on the feedback that we're getting. Okay, so QED-C has built a quantum marketplace directory. If you go to the website, it's publicly facing. All the companies that present here on this forum will get a little video icon next to their name. Also, that you can see their YouTube video, as well as when you click on it, you can see the description of what they're offering to the market. And also, you go to our YouTube channel, see the prior webinars posted there. Either type in Quantum Marketplace in Google, or just go directly to youtube.com/Quantum Marketplace, and it'll take you directly there. Okay, some trends. So we've been in the QED-C, we've been getting a lot of feedback that there's confusion in the quantum networking space. And with that, we decided to run a series of these. And the first one we did last month, that one is already posted on YouTube. That was a fantastic webinar with a lot of attendance, and we got a lot of really good positive feedback. And today, whereas the one that we just did last month was really focused more on the potential, it was focused on the market itself. So we had leading advisory firms, and we had leading firms that are building product in the space, and then two big customers in the space. And so today what we're going to focus on is more into the actual companies that are making the products and one of the customers there. So not going to go into detail here, but just to give people a background, so what are some of the potential use cases? I mean, we have a very strong, high-speed, reliable, fiber optic communication internet today. So what does quantum do to that, right? So there's use cases potentially in enhancing security using a quantum-enabled internet. There's also the idea that networking quantum computers together to build their scale to get to million qubit fault-tolerant machines, that connecting these quantum computers together is a way to potentially get to that achievement. And then also, getting back to some unique use cases around distributed quantum entanglement, teleportation, blind quantum computing. You're going to hear some of that today. And then also distributed quantum sensing. There are some use cases there where passing qubits around could actually provide value to certain use cases. So what are some of these platform subsystems and technologies, right? We sometimes hear about PQC. That is post-quantum cryptography. That is to, basically, that's like next generation RSA based on mathematics to harden security in the future against quantum attacks from quantum computers once they get strong enough. But that's not a quantum technology, that's a mathematical technology. Another area that security has been contemplated is the QKD, which is quantum key distribution. That's based on physics, not mathematics, but keys need to be passed. We've got quantum entanglement, sources, detectors. We need quantum memory. Some of the companies here have that already. We need quantum repeaters. We need quantum transduction to be able to change states, connecting, say, a superconducting quantum computer to a photonic network. You would need something like that. There's also other devices here. I think Qunnect and a few others are going to talk about how do we make all of this work on an existing telecom infrastructure. So that's going to be very interesting to hear from them. Okay, so today we have Noel Goddard, the CEO of Qunnect. It's a pretty exciting company who's just recently raised more professional venture money. We've got Jim from Aliro, the CEO there. They've also raised money and have some exciting products. Johan, the CEO of Ki3. We've got Corey from Qubitekk, and we've got Gregory Cantor, the CEO of NuCrypt, and we have Matt Turlington from Verizon, who's going to talk about how Verizon is looking at potentially using or adding quantum networking to its existing fiber infrastructure. Okay, with that, let's get Noel up.
I am the CEO of Qunnect, and Qunnect is a company located in the Brooklyn Navy Yard, which innovates devices to transform existing telecom infrastructure into scalable quantum secure networks. And I underline scalable because that's something that we really focus on as a team. And you'll see that reflected in our product suite. So Qunnect launched the first commercial memory to be launched globally, we think, actually in September of 2021. It's shown here as the large rack mount unit that you see here. And it requires no external cooling or vacuum support. Why is this significant? Well, it's because when you start talking about quantum networking, one of the things that you need to consider is the fact that all of the equipment is going to be scattered along, unmanned stations and fiber hubs, where they need to be extremely robust and cannot have very delicate types of equipment like cryogenics and vacuum support, which are also energy intensive, actually scattered every 25 to 50 kilometers. So we've spent a lot of time as an organization thinking about how we can turn this innovation into something which actually supports quantum networking protocols. And the protocol that we're interested in supporting is called entanglement swapping. So for those of you who are following the Nobel Prize this year, there were a number of great articles that came out about entanglement and entanglement swapping. So entanglement swapping is the concept of taking pairs of photons which have never met each other, interfering one half of each one of those entangled pairs, and actually transferring information to the remaining two photons, one from each pair, onto the same mapped entanglement state. And what you need in order to do that are devices like the source that I have here with the little infinity sign, which produces a pair of photons. One goes to a swapping station from either side. You perform a Bell state measurement in the swapping station. And when you do so, the photons which remain from the two pairs that originated at the sources are now mapped onto the same entanglement state. Well, the problem is you'd like to be able to do something with them. And that's where quantum memories come in. So quantum memories were thought for quite some time now to be the sort of key enabling device to go towards what we all think of as a quantum repeater. And a quantum repeater, analogously, just to the same way that we think of digital repeaters, is a way to actually increase the distance over which you can distribute entangled pairs of photons over what we think of now like a normal network. And for those applications like what Mark just mentioned of quantum memories and quantum sensor nets, quantum computing, distributed quantum computing, and distributed quantum sensor nets, you need to be able to hold onto the photons so on demand you can actually give them to other parts of the network to do something. So Qunnect again launched this memory in September of 2021. But then we also realized that what we needed to do was to be able to support that with something that had very low interfacial loss to the memory in order to have something that, again, works well in the network. And that's how we came to the point of developing the rest of our product suite. So one of those devices is the source. So again, the source and the swapping station are necessary to be able to support entanglement swapping. The memory is there to be able to temporally control photons and do something with them later in the downstream protocol. And our source is a source which is based on spontaneous four-wave mixing. And right now is the only source on the market that is producing narrow line width photons, which has something to do with those interfacial losses that I mentioned. Ours is tunable from 50 to 500 megahertz. And we produce very high quality pairs of polarization entangled qubits at over 100 kilohertz in rate. But this isn't enough, because the problem is you want to do this over real infrastructure. And when you do that, you start to realize that what you actually need are local references and calibration tools in order to be able to make a network-wide system viable. So in order to do that, Qunnect came up with another series of instruments that we call these quantum support instruments. One of them is a very good wavelength reference that sits at every node. It's atomic based, similar to the fact that the memory and the source for Qunnect are also atomic based. You need a clock to be able to distribute the same timing reference across your network with extremely high precision, so sub-nanosecond. And that was the original role of QSync, but now QSync has evolved into something which also controls the other devices within our product suite. And then finally, you need to deal with the fact that sending data through real-world fiber is hard. And for Qunnect, which at present we use polarization qubits in all of our protocols, that requires us to have something that goes out and actually tests any fiber channel that you're going to use in real time for the types of polarization drift which are experienced by environmental perturbations and corrects for it. So again, just to roll through some of these challenges when you decide to take stuff out of the lab and put it into the real world, Qunnect is actually trying to do this like in the extreme. So as Mark mentioned before, we just closed our first funding round. Part of that funding round is intended to support a quantum network testbed being built in New York City. It is the orange loop that you see here originating from Qunnect headquarters and going through Brooklyn and Queens. I've put for scale the island of Manhattan next to it from Google Earth, so you can get a sense that this is like half the size of Manhattan. So significant in terms of distances. And if we can do it here, I can tell you that we can probably do quantum networking almost anywhere, because it's old infrastructure patched together, obviously never intended to host something like quantum information. So to review some of the major challenges, specialty cooling and vacuum is simply not practical for real world scalability. It doesn't mean it's not going to be out there, and it doesn't mean that it's not going to be in hybrid systems where you have long-term storage nodes and interfacing to computers, et cetera. However, if you need to put stuff every 25 to 50 kilometers, it's not going to be practical. If you are still going to do that, then you have to have instruments that also don't need somebody to tune them every 5 minutes. So instruments must be low maintenance and they have to be stable. That's hard for quantum equipment because everything requires high precision, at least in terms of photonics and optics. You also need to start focusing a lot on what inter-instrument losses are, or network to instrument losses are, because they compound very quickly in your network if you're talking about lots of nodes. So again, real world fiber was not meant to host quantum information. So one of the problems is that environmental perturbations like rush hour, or going through an aerial segment of fiber, which is flapping in the wind, or going underneath water, all of this has the tendency to actually change the birefringence in the fiber itself. So you need some way to compensate for that. And then, of course, the precision of quantum systems demand accurate local references, which is exactly why Qunnect's product suite in the second half of the products I showed you is all focused around the fact that you would like to have a solid wavelength reference at every node. You would like to have a solid timing reference at every node. And one reason you want the solid wavelength references is that the lasers which drive all of your equipment need to be locked to something. And right now, the OEM lasers at quantum-friendly wavelengths simply don't exist. So this is an open problem. That's something that's near and dear to Mark Wippich and the QED-C, who've developed a tool to try to gather information on the most used wavelengths across the field in different physical systems. So what we're doing at Qunnect is really pushing forward this idea of a necessity for being able to have real-time polarization compensation on networks. Is something which is good for QKD networks, is something which is good for time-bin qubit networks, and it's something which is good for polarization qubit networks. So it's effectively qubit agnostic. We've designed something with a very minimal insertion loss of less than 2 dB. There's very fast measurement and compensation across, very noisy fiber lines, which we've driven this on already. We are agnostic to which telecom band you would like to use this in. And it can be triggered via either setting a threshold or setting a schedule or actually just requesting something on demand. But to give you an idea of how it works, here's a noise spectrum with a certain types of frequency, which are those perturbations which are happening in any given fiber line. You can see the drift is something that looks like a big mess here, where the fidelity drops from what was 100% down to something as low as 50% within 6 minutes and fluctuates around these different things. When you click this instrument on and you say, I want to maintain a threshold, in this case of 95 or 94% or above, it actually locks the polarization at a level which is above that and continues to sample and try to maintain the polarization above it. And why this is important is because if you are trying to do any type of quantum transaction over fiber and things have now drifted in polarization and you're trying to now interfere 2 polarization qubits, you simply can't do it. So this is something we think is going to be very important to support quantum testbeds going forward. And we would like to get out there. So we are seeking customers for these instruments and partnerships. If you're interested in working with us, this is something that is ready to go and has been tested on several other fiber networks in New York State. We also are seeking partnerships with some of our other instrumentation. As I mentioned before, Qunnect just closed on $8 million, led by Airbus Ventures, Sandbox IQ, and Quantination also are significant participants in that. We are also seeking contract manufacturer intros for specialty optics assemblies. So many of our instruments, as you've seen in the CAD renderings, which I showed, look like research instruments because they are research instruments. We want to turn these into products. And products means that they have a good software interface to the world which we want to use them, which is the networking world. So we have job openings for software developers, EEs, optical engineers, etc. And if you would like to join us, we are currently a team of 12. We're hoping to grow to a team of 18 over the next few months. And just drop me an email on our contact @ and we look forward to hearing from you.
Hello, I'm Jim Ricotta, and I'm the CEO of Aliro Quantum, and we are all about quantum networking. We're a 3-year-old startup based in the Boston area. Our mission is to enable the first multi-purpose entanglement-based quantum networks. Our business model is software and services. We have many US venture capital firms as our investors from both the East Coast and the West Coast. And our customers are government organizations as well as commercial companies. We're a software company. We partner with the quantum hardware suppliers, like some of the ones on the webinar today. And of course, we also partner with classical networking suppliers who are key to building quantum networks, as well as some integrators that are getting more active. This is our building behind Harvard Stadium. We share it with 2 other quantum companies, so we're starting to call it Quantum Square. So now if you visit Boston, there's Harvard Square on one side of the river. On the other side of the river, there's Quantum Square. What makes Aliro really different is that we combine experts in quantum physics with people that have spent decades building the classical networking products that support the classical internet today. So our founder is on the upper left, Dr. Pri Narang. She's very well known in quantum circles on the faculty of both Harvard and UCLA. Over on the far right is Bruno Reisman, who many of you who are active in QED-C know. He has spent decades building large-scale service provider class classical networking products at places like Juniper and Lucent. And he also spent a couple of years before he came to Aliro over at Qubitekk in the Netherlands, where where his alma mater is. And he learned a lot about and thought a lot about quantum networks. So he brings a great perspective of both sides. The rest of us also spent decades at places like Cisco and Juniper building high capacity, high volume networking products. Mike Wood in particular is very key. He came recently and he came out of the world of secure software-defined wide area networking, which is very relevant for one of the key quantum networking use cases, which is secure communications. So our solution is called AliroNet, and these are the applications we enable. And again, the idea of an entanglement-based network is just like a TCP IP classical network, you can run many applications on it, not just one. A QKD network can only do QKD, but an entanglement-based network can do clustered quantum computing, secure communications via teleportation, connecting quantum sensors, and also eventually distributed quantum computing and the quantum internet. So what are the problems we're facing now? We all know that the encryption that we use today is going to be hackable by a quantum computer soon. We also know that quantum computers don't have enough scale to do really interesting algorithms. As Mark alluded to, networking sensors can provide a lot more resolution for different applications. And then finally, something that we are really focused on because of our background in classical networking, the internet wouldn't have taken off if every company had a different way of doing everything and there was no interoperability. We used to have trade shows focused on interoperability of classical networking gear. And so we think this is a particularly important topic, and we're trying to address it with our software platform. So the solutions to some of those problems are based on entanglement-based networks. So with AliroNet, you can teleport qubits, maybe in addition to using PQC to give you defense in depth for secure communications. That's in the upper left. In a data center, you can connect quantum computers to get more qubits available to your algorithm. In the bottom right, networking quantum sensors, and over on the left, eventually with repeaters and other advancements that are coming, connecting quantum computers around the world. So let's drill down into AliroNet. There's 4 software products here. Up on the upper left is our simulator. There are open source simulators out there, but we found them lacking, so we built our own. It is very accurate in modeling the behavior of quantum networks, including the protocols for things like entanglement establishment and distillation and swapping and teleportation, but it also has a lot of physics built into it, so it can accurately model devices like the memories that we heard about, or the laser sources or the photon detectors. So that's something that you can use to simulate a quantum network and how it's going to behave before you actually go procuring equipment. On the right are our software products that manage and run quantum networks. The orchestrator at the top is a console for managing components, bringing them on board, configuring them, and then the controller below it actually controls the software that's sitting on the devices to make the entanglement and the swapping and teleportation happen. The red squares at the bottom are Aliros. That's our operating system for quantum networks, and it sits right on top of it's software and sometimes firmware that sits on top of the quantum devices themselves, which are the gray boxes. These can be laser sources, photon detectors, optical switches, quantum memories, and many other things. And the important part of our business model is we are independent of the underlying quantum hardware, because we don't know, again, back to that interoperability point, no one knows which hardware is going to be a certain customer is going to want to use, and they may want to use a mix for different reasons. So we talk about the 3 operational modes of AliroNet. The first is emulation and simulation. So using software to design your network and then leading to emulation on actual hardware. Next comes the pilot mode, where you build a small multi-node network. And then comes deployment, where you're actually running an application like secure communications, let's say, on a network. Again, there's a lot of interest in quantum networks in the government organizations, with telecom providers, different kinds of enterprises, and there's integrators who are already actively involved. We saw that Accenture was on the last session, and in fact, we're working with Accenture on a very exciting quantum network project in Canada. It's in Quebec. It's in Sherbrooke initially, but plans to link Montreal, Quebec City, and Sherbrooke with a quantum network. We're working with some of the parts of the IC and the DoD, the DOE labs, and we have some other very exciting commercial quantum networks that we'll be able to talk about in the next couple of months. On the right, some of the companies we work with, and there'll be many more over the course of the next year. We're going to hear from Qubitekk. We just heard from Qunnect. Again, we're working with Accenture on this very exciting project in Canada, a commercial quantum network. And of course, the classical networking players play a key role in this as well. So Aliro's call to action: quantum networking is coming. It's totally different from classical networking. And you can read about it and study it. We encourage that, but there's no substitute for actually trying it and seeing how it works and what its limitations are and what its potential is. So we say, get in touch with us and start your quantum networking journey now with AliroNet. And I'll add another call to action, which is if you're a quantum physicist or a network engineer, and you want to be part of the next big revolution in networking and communications, go to our website and ping us. Thank you.
Okay, so hello everyone. My name is Johan Gestin. I am the CEO and co-founder of Ki3 Photonics, university spin-off from Montreal, Canada, that specialized in the generation and manipulation of quantum photonic signals, in particular for quantum networking applications. So if I'm here today is to tell you more about the nature of our activities and how we fit into the quantum ecosystem. So Ki3 Photonics builds hardware for the distribution of quantum resources. And for this to happen, we focus on three very important requirements, which are the universality, which means that Ki3 Photonics hardware aims to be compatible with many protocols and application use cases. The scalability, we build hardware components using integrated optics and off-the-shelf telecommunication components in order to be directly implementable with existing communication network infrastructures and architectures. And finally, we focus on multi-channel information processing, aiming to have the coexistence of classical and quantum channels within the same optical fiber. And for this to happen, we build a multi-channel source of photons. So this source can generate entangled photons that are distributed over an optical frequency comb. And by using integrated and telecom components, we can generate quantum signals over 50 ITU communication channels, spanning the S, C, and L bands of telecommunication. So this is really the key element for frequency multiplexing. And also the pulse nature of the source makes it an ideal candidate for the generation of high-dimensional quantum states. So as a takeaway here, this source is compact, works at room temperature, and telecom wavelength. We will take pre-order in Q1 2023 for shipping in Q3 2023. So this is for the generation of quantum signals. In terms of manipulation of quantum signals, we propose to use fiber-based interferometers, which are an excellent component to basically reduce the losses into your network. We stay all in fiber rather than going from fiber to chip or from fiber to free space. And with a special stabilization system that allows to stabilize the phase of interferometer with the same precision over the range 0 to 2 pi, this is the ideal component for highly stable temporal encoding, quantum state analysis, and stabilization of quantum signals. So, as a key takeaway here, our stable interferometers fit into a 2-unit 19-inch rack mount that can directly be implementable into telecommunication networks. We take pre-orders now for shipping in Q1 2023. So in terms of applications, we target quantum networking use cases, but also entanglement distribution or multi-user quantum key distribution. So here it's really thanks to the nature of our source that is basically generating quantum information on multiple channels that the notion of network can really make sense here. And to conclude, I'd like to mention that we'll soon have access to a commercial quantum testbed in the region of Quebec, Canada. So we want to use this testbed to generate, manipulate quantum information in a network configuration and invite some potential collaborators, for example, to test some specific use cases they might have in mind. Also, if early adopters as well as investors are interested to support the deployment of our hardware, you're very welcome to communicate with us. So if you need more specific information, you can go on our website, ki3photonics.com, or you can directly contact us at the following address. I am Johan Gestin, CEO and co-founder of Ki3 Photonics, and I thank you for your attention.
Qubitekk is a quantum networking company. We were also a founding member of QED-C, and we think QED-C is a valuable asset for the quantum industry. I'd like to thank Carl Williams for his vision, Celia for her leadership, and Mark for your efforts to make quantum marketplace such a benefit to all of us. We engage with QED-C for the benefit of the quantum industry. And it's a co-opetition, but the industry and the ecosystem for quantum is growing, and QED-C is very much a part of that, and it's great to be a member. Qubitekk is based in San Diego County. We've got 25 employees, about a dozen consultants that help us out. And we provide a full technology stack for the quantum networking. We're led by Dr. Duncan Earl, who's our president and CTO, with 18 years of work at quantum work at Oak Ridge National Labs. And we're the leading U.S. developer and manufacturer of quantum networking and quantum communications gear. We engage the design, manufacture, and scale of quantum hardware, technology, and software for secure, fully integrated quantum networking solutions. We've been around since 2014. About the first 5 years was focused on research and development for quantum entanglement, and that's our focus today. So we focus on the transfer and distribution of quantum entanglement states across fiber and free space networks. We have a number of different contracts with the federal government and with commercial entities, and the focus on fiber telecom and then free space networks. We've got an Air Force contract for quantum entanglement on drones, which is really interesting, and then an Army contract to harden our equipment for launch and communications in space. Our products start from development kits for academia and companies that are interested in learning more about quantum, all the way to quantum networking with our basic essentials kits, and then also all the way through to full quantum network systems, which we're doing at EPB in Chattanooga, Tennessee. Quantum security is a basic function and feature of our quantum networking systems. So you may have heard Jim Ingram, the VP of Strategic Research at EPB, speak at the last quantum networking marketplace. That quantum network implementation in Chattanooga, Tennessee will be up and running as what we believe is the first commercial quantum network for the quantum industry, led by the quantum industry. That will be up and running in early summer of next year, and that network will be capable to move the quantum industry forward. So we're building this for our colleagues in the quantum community. We want to know what your requirements are, what your use cases are. We're totally open to get your input, so you can contact me at information@qubitekk.com. We are growing like everyone else. We're in the process of a Series A raise and have a lot of interest, as everyone is seeing across the quantum industry. So we look forward to continuing to work with everybody on this call, as well as the quantum industry. Thank you.
Thanks. Hi, everyone. My name is Greg Cantor. I'm the CEO of NuCrypt. We are a company working to commercialize products that are at the interface of electronics, photonics, and quantum effects. We've been selling quantum instrumentation for a long time and have an experienced engineering staff that's been with the company, most of them for more than a decade. Our goal is to generate fiber optic quantum instrumentation that's easy to use, so that it certainly doesn't take a PhD to operate the kind of equipment that we'll show you today. An example of an early complete entanglement system that we introduced in 2010 and sent to Japan to do a show floor exhibit is shown here. And we were able to ship the system, unbox it, and be breaking the quantum barrier, meaning making measurements that are impossible with a classical system, in about an hour. So this is the system I'm going to primarily talk about today, and it's been improved and updated over the years. So here's an example of our suite of instrumentation. There's a single software control over all these boxes. We have an entangled photon source that has multiple channels, polarization analyzer, and correlation electronics. They're all cohesively controlled, allowing someone to make measurements that are normally complicated, like two-photon interference or quantum state tomography, very easily. If you look in the bottom corner here, we see an example of a tomographic state reconstruction. This is essentially the information about the quantum state, and we can derive important metrics like fidelity from this information. An important aspect of our system is that there is a fiber optic data link between the two correlation systems. So this means that they can be located in two different locations, and data can be shared in real time as well as commands. So a distributed system with quantum nodes in different locations can behave as if everything was just in one location. We also sell the instruments individually, and because we work with R&D engineers a lot, we routinely customize these systems for our customers. I'd like to point out one thing about our remote correlation source. Not only does this perform all the correlations you need and signal processing that you need to make measurements, it also has high-speed electrical outputs. So you can program it to output a high-speed trigger upon a particular correlation event happening, and that gives you an additional freedom to do feed-forward controlled quantum experiments, which we're not talking about in this demonstration, but is something that we could do. We have some complementary products as well, useful for general lab use, but also helpful for time bit entanglement. And our systems can be adjusted and ordered to produce time bit entanglement as well. So here's an example of our system control software. We have a GUI. There's a system configuration, alignment, and measurement control can all be controlled from this one window. Alignment is important if you want to account for the unknown polarization fluctuation of fiber. When you put these systems and connect them through long lengths of fiber, you just don't know what that's doing to the polarization. So this is a way of backing that out and being able to account for it. And that lets us get these kind of pretty two-photon interference curves that you see here. Here's another type of data that can be displayed on the screen. All this data is both displayed on the screen, but can also be stored in a log file so that you can look at it at a later time. Currently, most people use our systems to distribute entanglement between two locations, but of course, as we go forward, more complex experiments are going to be happening. A lot of them will use an intermediary node that does some kind of quantum interference or Bell state measurement, and our system is well suited to make this transition. For instance, our entangled photon sources can be rate lockable, so you can have two entangled photon sources in very different locations, and we can lock their rates together. That's a precursor for doing this kind of work. And this is an entanglement swapping case that you see here. It's not using a quantum memory, but it's on-the-fly entanglement swapping. So we also have performed a lot of complex demos, both in fiber and free space. Here's an example of a flight test we did with a 2.5 gigabit per second quantum noise enhanced encryption system. It's not the entanglement system I was talking about before, but it's an interesting demonstration. We had to handle very wide power fluctuations due to both turbulence and pointing and tracking errors, and automatically securely resync after each disruption. So that involves putting together a lot of different people's vendors' components together and making this large system work. We can be a resource for you if you have demonstrations like this that you'd like to perform as well. My information is shown in the bottom right-hand corner, so please contact me with any questions. Thanks.
I'm Matt Charlington. I'm an associate fellow with Verizon Product R&D, and we investigate new technologies such as quantum technologies for use in future services and products developed by Verizon. So with that, what are we doing with quantum technologies? You know, it's a little early to start talking about a nationwide network, but it's not too early to start working on laying the groundwork. So as Verizon, we're collaborating with consortia like QED-C, Qunnect, and we're finding companies through that so we can work together on developing quantum technologies. But we are a network provider. We build networks. That's what we do, whether it's wireline or wireless. And we want to provide secure communications to our customers, for example. And so we are evaluating things like QKD and PQC with various proofs of concept on real world fiber. And if you want to look at some of the press releases, there's some QR codes that you can take a picture of and go take a look at them later. But what I want to focus on is our fiber network, which has over 1 million fiber miles. And if we're talking about quantum networks, we're going to talk about optical fiber. And in order to make a large network, you're going to need a lot of optical fiber. And Verizon has that covered a lot in the US, but we are a worldwide company. So what does a quantum network look like? And it's interesting that I'm talking as a service provider. I usually talk to customers, but what's a quantum network going to look like? From our point of view, it's going to look like a classical network. The underlying technology, we don't know exactly what's going to be happening in those devices, and that's fine. We have a set of requirements, and the equipment must meet them. But the network itself will look like the classical network. You'll have metro areas filled with fiber, filled with customers, interconnecting quantum data for whatever use cases that is, maybe distributed quantum computing. At some point, you want to go from New York to Chicago. You got to top on long haul fiber there. So you're going to need some quantum repeaters. So you're just like today, if you want to go from New York to Chicago over fiber, you have amplifiers. On the classical networks, you're going to need quantum repeaters. At some point, this network is going to stack, and you're going to have lots of customers, lots of traffic flying. You're going to have some kind of routing and switching plan, and I'm anxious to see what they're doing in the standards to kind of build that up. But the bottom line is this quantum network will coexist with the classical network. It'll pass through the same central offices. It'll go over the same fiber bundles and hopefully over the same optical fiber as classical channels. So my hope here is to kind of lay the groundwork and say, we're going to build a quantum network when it's ready. Verizon will be there. But what do we need it to look like? What do we need the equipment to do? And there's going to be quantum requirements that have to be met, but there's also going to have to be standard telecom requirements that have to be met. And every device that goes into our network must meet a specification in the US called NEBS, and that covers things like space, power, heat dissipation, wide temperature operating ranges, wide humidity ranges. And that's so that a box we deploy, if it starts heating up, it doesn't bring down the network in the next rack over. So these quantum networking devices will also have to interface with our existing fiber, and Noel went into this a lot. I mean, this is real world fiber. It's been laid maybe for decades or for years. It's in conduits underneath the streets in Manhattan. It's aerial on poles in Boston. I mean, that's what we're going to have to live with. We can't change that. Also, there's always going to be backhoes digging up fiber. So you're going to have splices. You're going to have connector loss through COs. So all of that has to be factored in when you're developing your quantum transmission technologies. And I will say that obviously we want the quantum technologies to transmit in a low loss band like C or L. And we also, maybe this is a lot to ask, it's early, but I would like the quantum channel to fit into a wavelength in the C or L band alongside classical signals, because fiber is expensive, and you wouldn't necessarily want to burn a fiber for a low bandwidth, low revenue service. And I'm not saying that's what quantum will be, but at some point we'll have to talk about the revenue. And I think Noel mentioned maybe 25, 30, 50 kilometers. It would be awesome if we could put them in the same huts, the same shelters as our EDFAs, which are our fiber amplifiers. Maybe 80 kilometers, could be longer. If you could put those in the same, on the same fiber bundle in the same hut, that saves a lot of money. But the most important thing, and I've been doing this a long time, the most important thing is that the equipment and the network needs to be reliable and manageable. So it's all about alarming, it's all about provisioning, it's all about monitoring the performance, and there's standards on how these devices should operate from a management point of view. But that is key. If we can't manage it, if we can't provision it, we can't deploy it. So I want the listeners to think about that and focus on how can we make this quantum network easy to use. Hide the difficulties. I know there's a lot of difficulties in developing the technology, but let's hide that from the end user. So with that, this is my contact information. I'm Matt Turlington at Verizon. You can reach out to me. Thanks.
So let's go to the roundtable discussion. So there's a lot of discussion of what one can do today with quantum networking communications. So I'm gonna go with Noel, pretty outspoken in this area. What is the real future of quantum networking communication in, say, 10 plus years?
So thanks. I think that, when Mark says that I'm outspoken, of course, I think we're all aspirational. And I think that, as Mark was saying in this intro slides, I think it's very important when we're thinking about how we design networks to think about the internet the digital internet as we know it is a network that connects devices. And really, as we are trying to go towards what distributed entanglement technologies can do, it's all about connecting devices, whether those devices be quantum sensors, or whether those devices be quantum computers, or whether they be quantum processors before we get to quantum computers. All of that, I think, is the aspirational piece of where we are in terms of looking what a network can do.
Yeah.
But of course, the big name that's out there is the quantum internet. So in 10 plus years, let's hope that we have good foundations for that.
Yeah, great. Jim.
Well, the folks who developed the classical internet, they thought it was for FTP, right? And they never could have imagined services like Uber or Airbnb or some of the other things that we kind of take for granted. So one answer is we can't imagine what is going to be on top of this quantum network. But clearly, secure communications and clustering quantum computers and connecting quantum sensors those are things organizations want to do today, and they don't quite have all the pieces, but the pieces are coming together pretty quickly.
Yeah, great, thank you. Johan.
Yeah, I agree with what Noel and Jim are saying, and I think it's important in this case to see the potential. And there's actually a lot of work that are done from a lot of people working on different use cases of the quantum-enabled internet. And there are some people that are coming with some solution for distributed quantum storage, for example, for some private auctions and things like this. But I think it's really, really important to find some very important use cases in this case to demonstrate that quantum networking is going to be the future. And if we think about 50 years ago, how the classical internet was working, and you were wondering what would be the killer application, nobody would know that. So I think it's the same case with quantum networks.
Okay, great. Greg.
Yeah, I mean, I guess I would pretty much agree with everyone that we don't really know exactly what the kind of killer apps are going to be. It'll be some kind of connecting of quantum processors at some point. But that's going to be very, very hard. I want to make sure that, the kind of things that we're doing now are kind of showing that entanglement is being distributed, even with rudimentary quantum memories. To go where we are now to where we need to be to do those kinds of things there's a number of breakthroughs that are going to be required, and it's very hard to predict through 2 or 3 big breakthroughs. So I think we have to be modest and develop the infrastructure that we need, the things that we know we're going to need, so that we're ready as this technology develops, and it's going to develop and change a lot over time.
Yeah, thanks. And you guys have been in it for a while, so I appreciate the point. So Corey, when you answer this question, it'd be great if, you're one of the companies that actually has been selling gear as well, just like NuCrypt, right? And so who's buying your product now and for what? I mean, you don't have to name names, and everything else, but what use cases are people buying your product for today? I know it's early, but what are they buying it for today, and what are they telling you about the future?
Yeah, the majority of it, I think, is research and development at this point, in this stage of the game. And like everybody else said, we've got years to go before a killer use case comes up. I think getting quantum ready right now across both our networks, or sensing networks, both fiber and free space, is going to be really important to get us to where we need to be. So it's not only just PQC, it's also, the readiness factor of being prepared for the quantum revolution that's on its way.
Yeah, great. Okay, so thanks, Matt. So where are you spending money today? You're a customer, and you have customers that are going to be asking that Verizon have this capability down the road. At least that's what's been contemplated, right? So where are you spending money today?
So today, the topic of this is quantum networking. So I look at that. Your time frame is pretty good. So if we're talking about quantum repeaters, quantum internet, we're not spending money today, right? Because it doesn't exist. So what are we doing today? We're looking at maybe let's take the government mandates, for example, on when you need to enact PQC or some kind of secure communications. So we're following that, and we're investing money in developing products that meet those standards. And so part of the way we're spending money now is doing proofs of concept, and that I think I mentioned before, it could be QKD, it could be PQC, but if we're going to be a government contractor, we have to follow the government's rules on terms of how to offer secure communication services. So that's what if you're asking about money, that's what we're focused on now. If you're asking about thought and time, well, we're looking to the future of quantum networking, and we see that as there's going to be at some point there's going to be, you have to use this to have a competitive advantage. If you're a large financial organization and you want to beat the other guy, well, you use quantum computers. And if you can't do that on one quantum computer and you need to network it, well, you need to network it. And that's exactly what we do with enterprises today. They use our services to gain a competitive advantage. So
yeah, great. Thanks for adding that extra color on that. That leads right into this particular question. So this, without even getting too fancy, right? Just one of the things that's been contemplated quite a bit by opinion leaders is sooner or later, quantum computers are going to need to be potentially connected. Is this a real use case? And I think we're hearing that it is, but I'd like to go back to Noel and get your sort of, is this the first one that's really going beyond the research? Is this one of the first ones that you think, realize it's early, but is this one of the first ones you think that actually is going to happen because of need, or do you disagree?
Well, I would say that so it's different to ask if it's the first or if it's valuable. So it's absolutely valuable. I doubt that it will be the first, right? So I think that what we see in quantum networking right now is that they sort of add-on that it does to compared to digital networking, right? Quantum networking cannot compete with speed. It cannot compete with bandwidth. It cannot compete with all of what we traditionally think are drivers in networking. However, it can compete on security. So anything that you can afford to send slowly, but has to be ultra secure, is the first applications, right? So I actually think that the first early valuable use cases will not be all that different than for distributed entanglement technologies as it was for what we would call point-to-point QKD systems. So I think that it is very likely that you will see a whole generation of sort of key distribution, but using entanglement-based networks and technologies as the first use case. And then, of course, the dream of connecting quantum computers will be downstream. The only way that wins is if the processors which are currently being developed today do not scale faster than what you could gain via connecting two small processors or multiple small processors in terms of a distributed network.
Yeah, great. Thank you. Johan.
Yeah, I agree with that. And I also want to mention that, it's not going to be very early that quantum processors or quantum computers are going to be connected because there's a lot of work to do in transduction. So having the signal coming from the quantum computer and transfer this signal into the optical domain, because basically the optical domain is the way we want to use the optical fibers in order to communicate. So we already have this network that is in place. So optical fibers are, let's say, necessary to communicate. So there's a lot of work to be done in transduction. in terms of use cases, yeah, kind of blind computing and security for let's say processing information, and I think it's going to be one of the best use cases for that also. Yeah.
Great, Corey.
So I think we're laying the infrastructure for that to happen. Obviously, there's a lot of work just focused on quantum compute. And they need to get that up and running to a point where it's valuable for the use cases that they see. But setting the groundwork and the infrastructure up to have that quantum network ready for when that happens is an important job for all of us to get to a point where not only can we use it for timing, sensing, and other use cases and security that we see today, but that we're a valuable asset when quantum computers are ready.
Yeah, great, Greg.
Yeah, I think I agree. Quantum transduction is really the key issue here. And if that issue is solved, it's really no different going 10 meters to something in the same room or going a kilometer or so to something in the same building because of the very low loss of fibers. So yeah, there's a possibility for this, but the technology has to advance quite a bit to the point where we can do it.
Yep, Matt. Oh, you're on mute, Matt.
Sorry, you can hear me now, right?
You launched right in there, yeah. You were pretty animated.
Did you see the points I was making?
I was aliasing though.
Yeah, so I was saying this is kind of a data center question, or maybe I'll look at it from a provider point of view.
Well, you're going to provide this service, right? Contemplatedly, right?
Yeah, but if I have to deploy 2 boxes in the same site to provide a function, man, and we've done that, with gigantic core routers, but I would sure rather manage one device, work on the scalability, get that quantum computer bigger, and if I have to scale, do it for disaster recovery or do it in another site. Just the thought of having side-by-side boxes just connecting to provide scalability, you lose a lot of processing power in those parallel connections between the quantum computers, I would think. And again, I mean, this is quantum computing. It's completely different, but I would expect, like anything else, if you're connecting things, you're going to lose some scalability.
Right, but there are quantum computing companies today contemplating this happening so they can scale. Okay, Mike, and if you want, maybe if you want to answer this, or go ahead.
Oh, could I answer this, Mark?
Yeah, that's what I'm going to next is you.
Oh, sorry. Okay.
Jim, go ahead.
So I think there's no question that it's valuable to cluster quantum computers in a data center. Even if the qubits go from 100 to 1,000 in a year, having 8,000 at the disposal of an algorithm is better than 1,000. And anyone who does quantum computing algorithms will agree with that. So I think it's definitely useful. However, I think that as Noel said, I think secure physics-based security is going to be more valuable more quickly. You don't have the transduction step, and to match some of Matt's issues. It's true, we don't have repeaters yet, and we can't repeat every 80 kilometers, but there are metropolitan area networks where security is extremely important. One example is, between the White House, the Pentagon, and one of the intelligence agencies. That's a very, relatively small metropolitan area network. Another would be in Verizon's heart turf there, connecting the Federal Reserve of New York to banks in New York and New Jersey. Again, those are small networks. You don't need high bandwidth, and security is of the utmost importance.
Yeah, great. Thanks, Jim. Okay, this is sort of a 2-part question. In the interest of time, I'm going to just put it all out there as one. So your quantum networking solutions work with standard telecom fiber. That's sort of been the theme here. And that's already deployed worldwide today, right? So if we look at that, how do your solutions, so we've got that existing fiber infrastructure in the ground worldwide. So how do your solutions plan to work in conjunction with live classic network traffic. Most traffic is traveling, say, in the C-band, 1550. But Noel, I'm going to go back to you on this. You guys have a lot of thoughts on this. I think you were saying recently that you're, working to operate in the 1310 band, but, really focus on the second part of this question, because I think it's pretty much a standard idea that we're not going to rip up the telecom fiber infrastructure. We're going to try to piggyback onto it. That's really part of your business model, right?
Absolutely. Thank you. So yes, our devices work on standard telecom infrastructure. So that's our suite. We work in the O band. So the 1300s, as you were saying before, we can also work in the S band. We, for certain reasons, believe that it's actually more important to work away from where all the rest of the network traffic is. So if you're going to be communicating with single photons, you're not really going to want to have scattering from all of the other multiplex stuff, which is in the C and S and sometimes L bands, depending on where things are. Again, no standard has been set for this yet, but we believe that there's some compelling arguments to be further away, and you don't actually incur significant losses, depending on how frequently you put these repeaters, by working down in the 1300s.
Great. Johan.
Yeah, in our case, we choose to work in the C band, especially because it's easier to find components that are, let's say, massively deployed for classical telecommunication. So it's really the way of scaling our device is really to stay in this band. And how it's going to work with the classical network, so of course you can have dark fibers, use dark fibers, but there are not a lot of dark fibers available right now. So the idea is really maybe to try to use the classical techniques that are used in communication, like multiplexing, and use that in the quantum domain. So that's what we are trying to do with the source that we have. So really multiplexing the quantum signals and trying to limit the interaction that you have with the classical one.
Great. Greg, you want to add on that?
Yeah, so I agree. It's almost impossible. I would say it's impossible to have a single quantum channel in a fully populated C-band classical system. There's just too much scattering. One possible solution for relatively short distances would be to go to the O band. That dramatically reduces the scattering and allows you to coexist with some amount of classical power, some decent amount of classical power. I suppose a potential really long-term solution would be if holy fiber actually ever gets a very low loss, that would allow you then to send very long quantum signals. Of course, that's not here yet, but neither is the quantum technology. So those are there are options, but most likely you would have to at least scale back what you're doing on the classical channels. You can't just pretend like the quantum channel isn't there and send as much data as you possibly can classically. You're going to have to co-engineer these things to allow them to work.
Great. Corey, you want to add on that?
Don't really have a whole lot to add there. I mean, we're working with a couple of our customers right now on multiplexing both classical and quantum channels. It's a hard problem, and but it is interesting. A lot of people see the benefit of it, but at this point, I don't have anything else to add.
Okay, great. Thanks, Matt. How are you looking at this with what was just said?
So, okay, first of all, you have to understand, as Verizon, we're supposed to ask for impossible things from vendors. So my wish list was obviously, fit it in the C-band next, 100 gigahertz away from a huge powered laser. And of course, that's a wish list because it makes it easier for us to deploy. And that's what we're always going to do. So, I mean, the point is we have lots of fiber out there. We're obviously not going to dig it up. So it has to work on buried and aerial fiber. And, going into other bands, I mean, that's a possibility. You have to add a combiner, splitter, take some loss. That would have to be engineered, or you move it on to a dark fiber. And, when you lay fiber, you're laying high count fiber, and there's possibly dark fiber out and about, but then you have to justify the cost to burn a dark fiber for maybe a low bandwidth security scenario, but we may be driven to do that, right? Because customers may demand that. So, all I can say is, the answer to the question is will it work on deployed fiber? Well, the answer is yes, it has to. And how we work around what's already on the fiber or how we move it to other fibers, we'll have to talk about that.
Right, and you could potentially use dark fiber with nothing on it in certain use cases if your customers are paying for it, right?
Right, but the thing to look at there is the fiber is essentially a piece of real estate, and do you use it for something and then kind of incur that cost of using it for something else? And that's why we have accounting departments.
Yeah, right. So Jim, so correct me if I'm wrong, but I understand you guys are really doing the software orchestration that makes all this work with APIs tying into all this hardware. How do you see this?
Yeah, so we're involved in some of the standards efforts in this area, through the QED-C and some of the groups. I think it's a hard problem, and I think this is a great example, getting the different organizations together, the different makers of hardware and companies like ours doing the management software and service providers like Verizon. This is the way we're gonna figure out problems like this, because this is another example of a multi-vendor interoperability kind of problem.
Yeah, totally agree. Thanks for that, Jim. So, okay, so just without going, I have another question that's really important after this one too, but just, in terms of the technology, and I want to go back to Noel again, I listed all those standard, quantum networking, sort of solution modules like memory repeaters, transduction, sources, entanglement sources, detection. Those are all the building blocks. And then, of course, Aliro's software to sort of orchestrate it all on, say, a Verizon or other network. Now, you're also making gear that allows those devices to work on the classic network in conjunction. So with that, I know you've already talked about that, but what other technology gaps do we have that need to be addressed, or what are some of the real sticky points right now, just technologies wise, not getting into standards and stuff like that yet?
So all of our instruments are driven by lasers.
Oh, here we go.
and on the back end, in order to do any type of work at telecom, you start to cross into a problem with detectors. So I would say for all of the good stuff that we build in between, you always have challenges in the laser market and the detector market, and there's lots of great companies in both, but they have to be actually incentivized to develop things which support our market. It's very difficult when there's not a lot of deployed hardware out there right now and no standards which justify bringing down the cost of lasers. For instance, Qunnect, when we do basic research, we use research lasers. We would like to have OEM lasers in order to make our products more affordable. Similarly, on the back-end detector side, everybody knows that cryogenic detectors are premier. Nanowires are in every research lab in the country that's doing quantum this way. But we aren't going to be deploying them everywhere unless the technology improves considerably to have cryogenic deployed nanowires someplace, or detectors which do not require cryogenics in order to make these things work. So an ongoing project at Qunnect is our room temperature, no cryogenics, swapping station, exactly for that reason. But I think that we have to look at the other two ends when we talk about networking.
Yeah. Johan, you want to add to that?
Yeah, I totally agree with Noel that detectors are kind of a pain point for now. But one of the things also that we have to think about, I think, is try to increase the rate of transmission of the qubits, their resistance to the noise, and for this there are potentially a solution that using high dimensional quantum states and things like this that could also interact also easier with the quantum memories, actually.
What was the last thing you said? Quantum what?
Quantum memories, quantum repeaters.
Quantum memories. Yeah, right. Great. Greg, you want to add on that?
Yeah, I guess in the near term, I mean, I think everybody wants better and better quantum memory. So clearly that's a key issue, a key thing that's needed for networking. In the longer term, solving this quantum transduction problem, in other words, getting light from the photon into, say, a processing chip, that is probably going to be a big game changer, allowing periodic processing and maybe error correction and things of that nature. So that's something that may be required to really go to the next step beyond what we can do today.
I totally agree. Transduction is fundamentally key. RF to photon, photon to RF, and then in mass to energy back and forth. These are really hard problems. Mainly university level research right now. There are a few companies now though that are going after it, at least establishing links. I want to flip this on its head a little bit and go to Jim. So from the software and the API perspective, anything Aliro sees there in terms of technology gaps?
Well, I certainly agree with all the ones that have been then cited. I think addressing the issue that Matt brings up with the 80 kilometers is probably one of the big things, and some of that can be done with at the hardware level with, let's say, better memories or that sort of thing, and then some of it is going to be innovation at the protocol level with purification and swapping protocols that can make more of the entanglements that are generated. Yeah,
okay. And then Matt, you want to add on that?
Yeah, I'll let the technologists, talk about the lasers and the detectors. But one thing I'm really curious about and interested in is working with somebody, as like Noel said, you got to escape the lab somehow and get into the real wild world. So what I want to know is, what do I have to do to compensate for polarization or extra loss or transient conditions? She mentioned flapping in the wind or lightning strikes. And well, you don't want to drop a huge, high bandwidth, signal if you get a lightning strike on a fiber. But and one thing we haven't really talked about is timing. Timing is a big issue in telco networks, and typically they're timed off GPS with nanosecond type resolution. What do we need for quantum, and is that going to add a timing synchronization layer?
Okay,
right.
So that leads me into the final question here, and then we're gonna
Mark, if I could just add one thing. It's not on the
go ahead.
Technology realm, but it is on a gap, and that's our supply chain, which is really important to the whole industry. And to me, that's a gap, as well as something that Celia brought up, and that's the transfer of technology between countries, which is also a key gap at this point.
So yeah, and the spirit of that leads both you and Matt sort of spirited right into the next question. So, sort of beyond the technology, right? So what else is needed to enable, accelerate quantum networking, right? And this is really a three-pillared piece here that, much debate inside of QED-C, and I'm sure outside of QED-C member companies, is really what's the real need and benefit of having commercial quantum network test beds, standards in metrology, where are we at with that? How much do we need that? And then how about the companies themselves here partnering among the various players in the ecosystem? That's what we're trying to, that's what we work to facilitate in the quantum marketplace. But I'd really like to just kick this off again with Noel is how are you seeing these critical issues, right? And what are you doing about it?
So I think test beds is a very interesting one to start off with, because Europe really accelerated their launch of a number of test beds much earlier than the US. And the US decided to follow a strategy of creating test beds that typically had an academic anchor as sort of their first rollout. Those are two very different types of initiatives. In Europe, you were seeing something that was more centrally funded. And again, so this is the Euro QCI initiative. Basically, they're trying to build networks in every country, which are supported through the EU, which eventually are all supposed to connect to each other. It's a much more open system for actually being able to supply to them as a vendor, as versus academically anchored test beds, where very often the reason for them being anchored at an academic institution is because they're supposed to prove out the academic technology. So that's not necessarily something which is open to a broad series of vendors. So I think the best value of a commercial quantum network testbed or an open quantum network testbed is the ability for many vendors to come together and to start testing some of the stuff which has been highlighted as a theme for everyone, right? The Jim threw out the word interoperability. That's really something that as an industry, we're still very much struggling with, because all of our technologies evolve in parallel, but they're based on different physical systems. And all of those physical systems have favorite wavelengths, et cetera. So if we're going to learn how to play together, it's those types of network testbeds where we're going to actually find that interfacing. Then I think, NIST is another good example with the DC QNet, which is coming online, which is built largely for this idea of metrology of quantum networking tools. So that will be another sort of government-funded, US-based open testbed where vendors can actually test and see, again, how well they interface with other types of equipment. And that connects 5 different agencies in the DC area. That's something which in the QED-C earlier presentations, right, has been something which has been a focus of announcement, and everybody's sort of anxious to see that come online. And then close partnering, I think you'll find that a lot of people on this call already have some types of partnering between the companies. For obvious reasons, we all want this to be something that works in the end, and it's very difficult to be ambitious enough to develop everything yourself. It's just not the way companies work, right? So.
Right. Johan, you're involved with a commercial testbed in Canada, you mentioned. Can you expand on that and then address the rest of this, how you see it?
Yeah, exactly. So yeah, I think it's going to be one of the first commercial testbed in Canada. So it's going to be based in Sherbrooke initially, and then it's going to try to connect with Montreal and another city in Laval. So the idea is really to try to bring people from the tech community, not doing that much research on that testbed, but really trying to test, to collaborate with potential partner, like for example Aliro, that I know that they are planning to be there also. So how the hardware is communicating with the software part, and how can we work together to make it work? Because I think also if you wanted to build a quantum-enabled internet, this is not one company that is going to be able to do that. We're going to have to do it with other people, because you cannot be expert in networking, software and hardware and everything. It's going to be very difficult. So we really have to work together. And those kind of commercial testbeds, I think, are really important to demonstrate also to potential users like banks or other companies that what we are doing is important, that it's work, that by working together, we can build a network at a bigger scale, let's say.
Yeah. And Corey, can you add on this? I know some of that was talked about in the last, you involved in anything around that too, or you want to wait with that?
No, I think commercial networking obviously is going to be really important. It's, a lot of money from the federal government has been pumped into the national labs and the work that they're doing, but to have a commercial entity that allows for, as a quantum service provider, I think is going to be important to come in to do, an experiment or to have a long-term project to figure out. But I also think that interface capability is going to be extremely important for the industry to get standardization. It's going to take that type of testing and interface capabilities to see what actually works and where the standards need to lie in the future.
Right, because we got to build the commercial quantum network testbeds so that we can help define the standards and build the metrology, right? Because some of the metrology doesn't even really exist yet for this hardware, or am I incorrect?
It doesn't exist. Yeah.
Yeah, it doesn't, right? Okay. Matt, how would you look at what do you want to see? How do you see these three things?
Well, yeah. So I think as a provider, I would be a little leery of buying a product that was tested on spool fiber in the labs, right? So I think test beds are, well, yeah. I mean, and Noel talked about, the differences when you get out in the real world, and you don't see that on spool fiber. So I think the test beds are important because they provide network providers and they provide equipment providers a way to evaluate this new technology, which I'll be honest, I don't know exactly how it's going to work on real world fiber or how far you can go. And that work could be fed directly into standards bodies and to develop metrology to measure polarization or dispersion or things like that happen on these quantum channels that we don't measure or have to measure on classical channels. I mean, with brute force, we send a gazillion photons, and okay, so you lose some, you get enough at the other end. But this is a different case, and the metrology will be different, the standards will be different, and you have to do that by getting input from real world tests. And in order to get real world tests, you have to talk to maybe a telco or a fiber provider. So I think these are all very important.
Yeah, thank you, Greg.
Yeah, I mean, I totally agree with what everyone said. These test beds are critical. And one thing is that it's very important, I think, for them to be long-term funded so that people can make plans and make investments to continue to improve the technology. And it should be run by someone, whether it's a commercial entity or a government entity, that's not building the actual components being used, so that they're agnostic to the technologies. They're incorporating whatever the best components and the best technology is as it develops. So you definitely want that kind of third-party perspective in running these networks.
Yep. Thank you. Jim.
Yeah, so I see these three as a sequence. So the first thing you need are commercial quantum networking test beds. That leads to number three, because really, in my experience with startups, which goes back, several decades, you really only learn how to work together when you have a project that has a budget and milestones and deliverables. So you need the test bed for the vendors to work together. And then the standards come last, because as we learned in the classical internet, you want to be able to try things and see what works, as Matt said, before you say that's the standard. We talk to service providers, and we believe there's a business in running a quantum network testbed. And a lot of the service providers are coming to this realization, because what we all discussed in this webinar is that quantum networks are hard. And those organizations that can put a small network together and offer access to it, there's a business model there. We call it Quantum Lab as a Service. And Mark, since you asked me to do a product pitch today, I'll just add one more product thing, which is that the Aliro Orchestrator. Not only does it help you manage the network and alarm it and make sure things are working, but it's got the notion of users and accounts and design of experiments, validation of experiments. So it's got a lot built into it that a service provider can use to open it up. It even will send data to the OSS/BSS, which is the billing system, right? So that's something that we saw a while ago and have put that into our product.
That's awesome. So your orchestration is really for production networks, but it's also for developing networks, right? So
that's right. You can offer it as a service, yeah.
Yeah, great.
I will say billing systems are a lot more difficult to develop than quantum technologies. So.
Yeah, that's because accountants are involved.
Yeah, there you go. Okay.
Very difficult, yes.
All right. Thank you, everybody. I'm going to call it a wrap there on that. And so just a quick snapshot. The next quantum marketplace that we're looking at is going into quantum law on December 13th. And then also we're going to come back in 2023 and touch on quantum network test beds and other network topics. With that, Celia, do you want to add anything?
No, this has been another great session, and glad that we recorded it so we can all go back and mine it for nuggets going forward. And, please share with your networks information about the Quantum Marketplace program. We continue to grow the community and I think perform a real service. So thank you everyone for participating.